Are we broadcasting? Good. Well, we will start by briefly talking about what happens when we take the product of two spaces or several spaces, and the first main result is the functors which take the couple xy to the singular chain complex of x cross y, and the other one which takes xy to singular chains of y, of x, tensor singular chains of y are homotopy equivalent. Well, before we talk about the proof, let's see if we understand what it says on the board. Singular chain complex is something we have already seen, but what is the tensor product? Does everyone know what the tensor product of two chain complexes is? Yes, no, mostly.
Like in differential, we have some -1 to the power.
Yeah, so let's review the tensor product. We start with two chain complexes of abelian groups. The tensor product is another chain complex, and the nth component is the sum of the tensor products for p plus q equal n. Then the tensor product is the differential the tensor product is again a chain complex. The nth component is given by this formula, and the differential acts as by the next formula, and basically the formula is the Leibniz rule, and the sign here and the sign here, which is +1, are not really important. Basically, if we put some other signs here and here, such that delta squared is 0, we will get a chain complex which is even isomorphic to the one given by this formula. So there is no deep meaning in -1 to the degree of A. Okay, so now I understand what this means. And in both cases we have functors. I have defined the values of the functors on the objects, but it's straightforward to define the functors on the maps. Now, what does it mean that two functors are chain homotype equivalent? Well, first of all, we need to have natural transformations going in both directions, namely natural transformation from the first functor to the second, and vice versa, from the second to the first. Does everyone know what natural transformation is? Okay. Okay, I will erase this formula and basically the formula is a variant of the Leibniz rule with signs. If you remember the Leibniz rule for differentiating the product of two functions, then this formula is very similar, except there are signs, to make sure that d squared is 0. A natural transformation between two functors is a collection of maps or morphisms. Let me say from where to where. Tau x goes from fx to gx, and such that for all x, for all f in C of xy, the following diagram computes. So we have f of x, f of f, f of y, and similarly for g. Can someone give me an example of a natural transformation? Well, there's always the identity natural transformation, but it's not particularly interesting. Are there any more examples? Just any example of a natural transformation, apart from the identity transformation, which is sort of too simple.
Maybe you have fundamental growth functor with different points.
Okay, so the fundamental group is a functor from which category? Okay, so pointed spaces. Pointed spaces from pointed spaces to groups. Well, this is one functor. And what's the other functor? We need two functors. Yes, but this works if we have a fixed space and choose different base points. Sorry, finite. Which functor? Well, let's do something simple. For example, let's take we could take vector spaces as both C and D, and we could take the first functor to be the identity functor, and the second one the functor which takes a space to its double dual. Now, we know that for finite dimensional spaces there is a natural isomorphism between a space and the double dual. But for infinite dimensional spaces, the double dual is quite a bit larger than the space itself. But still we have a natural map from the space to the double dual. And as you can check, this map is a natural transformation. Does this make sense? Well, obviously there are many more examples. Okay, so this statement, which I've written here, claims, firstly, that there are natural transformations. Of functors from the category of couples of topological spaces to the category of chain complexes. And moreover, Okay, both compositions are natural transformations. If I compose two natural transformations, I get a natural transformation. And I also have the identity natural transformation. And my claim is the compositions are chain homotopic to the identity natural transformation. Does this make sense? What does it mean that two transformations, for example, of this functor, are chain homotopic? Well, if we have if we have two maps, two chain maps of chain complexes, then to say that those are chain homotopic is the same is the same as to say that there is a D such that where D is so F G C1 from C1 to C2 are chain maps. Now D well, D is not a chain map. D is just a collection of maps of abelian groups. Well, suppose now these D's can be chosen in a functorial way. In other words, suppose we were able to construct such a D for every couple X and Y. Well, first of all, F is the identity. G is some natural transformation. We don't yet know what it is. The difference is delta D plus D delta. But suppose we were able to construct a D, not just for in some way for each X and Y individually, but suppose we're able to construct a D which would be a natural transformation. or since we have graded objects, a collection of natural transformations. Transformations from what? Of functors from couples of topological spaces to graded vector spaces. And this is the meaning of this is the meaning of the phrase two transformations are chain homotopic two transformations are chain homotopic as transformations. In other words, the chain homotopy D can be chosen to be a natural transformation. Not just a random D for each x, y individually, but a D which would be a natural transformation. Okay, now the proof of this proposition, the easiest proof of this proposition that I am aware of, uses acyclic models, and it's in the course Google folder. A few weeks ago we talked about another statement, namely the excision property, which again can be proved in different ways, but the shortest option is to use acyclic models. And then we said let's relegate this to the lecture notes. And I suggest we do the same for this proposition. Basically, I think the proof of the acyclic model theorem is something one has a better chance of understanding on their own, without anyone watching and without anyone trying to explain it. If anyone tries to explain it, this would only make things worse, not better. Anyhow. So let me just say that the proof The proof is in the lecture notes, which are in the Google folder. Corollary. We have an isomorphism. X cross Y tensor G P plus Q equal N HP of X with basically we have two isomorphisms. One for homology, the other one for cohomology. Well, I will first write them down. And then let's see if we understand what this means. X and Y are spaces. G is an abelian group. My claim is there are these two isomorphisms which express the cohomology of X cross Y and the homology of X cross Y with coefficients in G in terms of the homology of X, respectively the cohomology of X with coefficients in the cohomology of with the coefficients in the homology of Y, respectively the cohomology of Y. Let's see an example. Again, the proof is in the lecture notes.
This looks sort of strange to me. The G homology group. No, the homology group with coefficient G is the same as homology group in the coefficient with other homology groups, or it makes it for me it would look more natural if that on the right hand side each summand is tensor product of homology group in G respectively to X and Y.
Well, this would look more natural, but it would also be false. Let's do an example. Let's take x equal y equal RP2. Okay, so first of all, we need to calculate the homology of RP2. And first of all, we consider the homology with z coefficients. And as everyone probably knows, or at least that's my hope, the answer is this. Well, we also need the homology mod 2. In other words, the homology with coefficients in z by 2. And again, the answer is what? Well, what do we have in degree 0? Z by 2. Correct. What do we have in degree 1? Again, z by 2. What do we have in degree 2? У меня такое ощущение, что никто не смотрел листочки с задачами. Вот, и это очень плохо. Нужно решать задачи и спрашивать меня, если что-то вдруг не получается. So, what do we have in degree 2? Well, no, we don't have 0. We have another z by 2, which could also be seen by just applying the universal coefficient formula. This z by 2 is a tour of this z by 2 and z by 2. Okay, so we have all ingredients. So we apply the first formula. And we want to calculate the integral homology groups of RP2 times RP2. Now, it would be the answer would be more well, the formula would be easier to apply if we make a table of the following type. So let me write down the following table. In the 0th row, I put these groups, and in the first row I will put these groups. Now, to apply the formula, I just take the sum of all the groups which occur in the diagonal p plus q equal m. So I have 4 diagonals. I have the diagonal p plus q equals 0, then p plus q equal 1, p plus q equal 2, p plus q equal 3. And the answer is I have z in degree 0, then z by 2 plus z by 2 in degree 1. Then I have z by 2 in degree 3. And then I have another z by 2 in degree 4. Does everyone agree? Now, the reason I've written the groups as a table like this is that this is the second page of the Luray spectral sequence of the projection RP2 cross RP2 to RP2. So, side remark. This is the second page of the Luray spectral sequence. Well, now let's see what happens if let's see what happens if I take the tensor product of the homology of RP2 with itself. In other words, the tensor product of the homology of RP2 and the homology of RP2. I know the homology of RP2. It's z by 2. Now, what happens if I take the tensor product? Well, the answer is I get z in degree 0, z by 2 plus z by 2 in degree 1, and z by 2 in degree 2. Oh, sorry, this is nonsense. 1, 2, 3. I can't count to 3, but now I can. 0, 1, 2, 3. Simple. Anyway, so the difference between this and this is that here we have an extra z by 2 in degree 3, and here we don't have it. Do you understand? So the tensor product of the two homology groups sometimes gives the right answer, but not always. And there is a similar recipe which works for cohomology. And again, for cohomology, the tensor product of the graded groups is not the same as the cohomology of RP2 cross RP2 with Z coefficients. Так, понятно ли, что вообще происходит, или Окей, то есть что-то понятно. Это хорошо. Okay. Well, do you want me to do the cohomology example or not really? Okay. And well, in a short while we will see another way of calculating the a similar but slightly different way of calculating the cohomology of the product. Basically, to the ingredient that we're still missing is the product on the cohomology. So let's talk a little about that. Well, let's, well, to begin with, I will start by saying some general motivational things which formally can be skipped or ignored. So I will explain what the product on cohomology is, but first of all, why should one hope to have any sort of product on cohomology? Well, firstly, not every space has a reasonable product structure. There are spaces such as Lie groups for which we have a product, or topological groups, H spaces, and so on and so forth. But not all spaces are like that. So we can't really get a product on we don't really have a functorial product on spaces, which is well, which is slightly disappointing. But on the other hand, and this is well, if we this is something this is the next thing to think about once we've realized there is no product. Okay, there is no product, fine, but is there a co-product? And the answer is yes. Every space is a comonoid. Well, what's a comonoid? I don't want to talk in detail about monoidal categories, but just a little. What's a monoidal category? Well, it's a category, and this category is equipped with a tensor product and the unit of the tensor product, which behave in a reasonable way. And once we have a monoidal categories, we can form monoids. Basically, to have a monoid, we need to have a map from a morphism from the tensor product M tensor M to M itself. Well, this is not surprising. But also we need to have some sort of extra condition which corresponds to the fact that a monoid has a unit. Well, in the classical case, a group is a monoid which also has inverses. But a monoid is required to have a unit. Well, Now, what is a unit? Well, in fact, a unit is a morphism from the unit of the tensor product, which is an object of C, to M. And we also require that some diagrams commute. And those diagrams correspond basically to the fact that this unit is a unit. Would you like me to draw those diagrams? Well, let's draw them. So I have M. So M is an object of C. Okay, so I have the multiplication. But I also have this morphism from I to M, and I have the identity morphism from M to M. So I tensor product these two morphisms. I get a morphism from from M cross I, or M tensor I to M tensor M. I is a monoidal unit, so I have this natural isomorphism, and I also have the identity morphism from M to M. And I simply require that this diagram should commute. Okay, and there is a similar diagram when I transpose I and M. Okay. Now this basically says that we have a product on M, and we have a unit for this product. Now it makes sense for a monoid to be associative, and it makes sense for a monoid to be commutative. So there are associativity, the associativity properties and these are expressed by requiring some more diagrams to commute. Would you like me to draw those? Well, If you do, then please let me know. Otherwise, I'll just I'll just say that there are many examples of monoids. A monoid in sets is just the usual notion of a monoid. A monoid in topological spaces is basically a topological monoid. I don't know any other name for it. A monoid in vector spaces is an algebra, and then these conditions correspond to associative algebras and commutative algebras and so on. And so on and so forth. There are lots of examples of monoids, but nothing prevents us from doing it the other way around. We still keep the monoidal category. In fact, there is a way to think of a monoidal category as a co-monoidal category, but never mind that. We keep the monoidal category. So we have the tensor product and the unit. What's a co-monoid? There's a similar diagram to this one with M and I transposed. Okay, so what's a comonoid? Well, I need to invert all the arrows. Well, instead of having an arrow from M to M, I start with an object C, an arrow from C to C tensor C, and what? And a co-unit. So this is the co-product. And this is the co-unit. And then I require that the same diagram with all arrows reversed. Should commute. With arrows reversed. Okay, now why do we need this? You probably have guessed already. I want to make an arbitrary topological space, not necessarily a Lie group, into a co-monoid. Well, what do? I have the standard monoidal structure on topological spaces. So now let me take C equal top. Then the tensor product is just the usual Cartesian product. The unit of the tensor product is just the one-point space. And then for every x, I have the diagonal map, which goes from x to x squared. I also have the unique map from x to pt, the one-point space. And all this makes x, so this data makes x into an associative, in the monoidal case, there is always a co. So instead of associative monoids, we talk associative comonoids, we say co-associative comonoid. And the same with commutativity. So this data makes x into a co-associative co-commutative monoid on top. And this is the idea behind the product on cohomology. Not every space is a monoid. Oh, sorry, comonoid. I'm sorry. Comonoid, co-associative, co-commutative, comonoid. Every space is one, but not every space is a monoid, associative, commutative, or otherwise. Okay. And here is why if we want a ring structure, not a co-ring structure, but a ring structure, we need to have cohomology, not homology. Why? Because we have a natural comonoid structure and no monoid structure on every space. Okay, so this was the motivational part. It can be ignored, but still I think it's useful. So now I suggest we have a break, and then we'll talk about the product in more detail. Every space is a co-associative, co-commutative monoid. Let's try to extract some useful properties from this observation. First of all, let's try what Alice suggested. Let's try to see whether or not the singular chains of a space are a co-ring. Well, we need to use the diagonal map. Actually, let's be more precise. We have the diagonal map on the level of spaces. So we have one for chains. No surprises there. And we can compose this map with with the map from the chains on the product to the product of the chains. We don't know what this map is, but we know it exists. And we get a co-ring structure on the singular chains. This co-ring will this co-ring will be in general, well, it will be something. The definition involves this map that we don't know. And the co-product on the level of spaces is both commutative and associative, or more precisely, co-commutative, co-associative. Correct. But the one we get on the level of singular chains is in general neither. Why? Well, because we arrive here and not here. In fact, there is a way to choose this map so that the resulting map from C lower star to C lower star squared would be co-associative. I'll talk about this a bit later. But not but it will not be co-commutative. Okay, but this is not the main problem. The main problem is we really want to have some sort of structure on homology or cohomology. Well, and there we run into a difficulty. There is a map from if we have C1, C2 chain complexes, then we have a map from the homology of C1 tens of the homology of C2 to the homology of C1 tensor C2. And this map will, in general, not be an isomorphism. Except in some special cases. For example, if all complexes are chain complexes of modules over a field, then this map is an isomorphism, but in general it isn't. So when we apply homology to this arrow, we get a map from the homology to of C lower star to the homology of the tensor product. We do not get a map to the tensor product of the homology of X with itself. So the homology of X with Z coefficients is not, in general, a co-ring in a sensible way, because this arrow goes in the wrong direction. The chains are a co-ring, but the homology is not. Well, let's see what happens when we try to do the same for cohomology. So this was first attempt. By the way, does everyone understand how this map works? No. Okay. Well, let's see. Suppose I have a cycle. Suppose I have a cycle in the first complex, and this means the differential is 0. Suppose I have a cycle in the second complex, then when I take the tensor product differential and I apply it to x tensor y, I get 0. Why? By the Leibniz formula. So the map takes x tensor the class of x tensor the class of y to the class of x tensor y. Alice, does this make sense?
Can you repeat this? I mean, the previous moments I just was writing then this I don't get you. Please repeat the last sentence.
Does this explanation make sense? The map from this graded abelian group to this graded abelian group does the following thing. It takes a cycle here, a cycle there. Well, we can choose representatives. Let's call those x and y. Let's.
Yeah, it's clear.
Okay. And it's a good exercise. Show by example that this map in general is not an isomorphism. Basically, we have already seen an example earlier today when we calculated the homology of RP2 cross RP2. Basically, if you take, for example, the cellular chain complex of RP2 as C1 and also as C2, you will get an example. So the map is there, but this map in general is not an isomorphism. Okay. So, Alice, do you understand now why the chains are a co-ring, but the homology is not a co-ring? То есть цепи – это кокольцо, а гомология – это не кокольцо. Кроме как если, значит, если все над полем. Ну или в каких-то других подобных случаях. Okay, so the first attempt didn't quite work. We get a co-ring structure on chains, but this is all. Second attempt. We try cohomology. Well, let me also take any ring with identity. Well, to begin with, let me start by just looking at singular cochains with coefficients in Z, and then we'll see how to include the ring. Okay. I want to map from C upper star of x to C upper star of tensor C upper star of x to C upper star of x. This would give me a co-product. Well, okay, C upper star of x is the same as Hom. C lower star of x, Z. Okay, I will draw some arrows and then I will explain those. Okay. First of all, in the chain case, I had a map from the chains of x to the chains of x tensor chains of x, just by using by identifying the chains on the square with the square of the chains, using some magical black box. Here, when I dualize, it is not true in general that the tensor product of the duals is the dual of the tensor product, but there is a map from here to here, which we will take a look at in a moment. Okay, so this map is this map is there. Here we have maps in both directions, because we know how to go from this group to this group and vice versa, and then we take common to Z, and we get maps in both directions. And then we finally apply the diagonal map. More precisely, the map induced by the diagonal map. So we what we get is the following thing. We see that the singular cochains of any space is a ring. Which we get using this diagram. Okay, let me explain this this arrow. Okay, let me explain what happens for abelian groups. Suppose A, B, C are abelian groups. Then I have a map from Hom A C times a Hom B C to Hom C. Okay. Does everyone understand what this map does? Yes. Or explicitly, if I have an F from A to C and a G from B to C, there's okay. So there's something wrong here. I need so if I have a map and another map, I can take the tensor product of of both maps, but then I need to multiply those, and here is y. And this is why I want to assume that I take maps not into just abelian groups, but into a ring. Okay, so if I have f and g, I have f tensor g, which goes from A tensor B to R tensor R. And then I just take the product on R and get an element here. Okay. Now, this map is in general not an isomorphism. Can one give me an example? Even if A and B are both free. Well, there are stupid examples where A and B are not free. Let's forget about those. Let's consider free ones. And basically well, the example is obtained by taking an infinite direct sum of z's. But the map is there. So now this all the same applies to chain complexes. So I have a map from this group to this group, which is a map of which is in general not an isomorphism, but the map is there, and then I use this arrow, which is straightforward, not straightforward, but we know it exists, and then I use the other arrow. But so we had a problem of sorts at this step, but the advantage of using homology sorry, cohomology is that we we get a ring structure on the cohomology, not just on cochains. Why? Well, here I have the tensor product of two complexes. When the tensor product of the cohomology, graded abelian groups, maps into the tensor in the cohomology of the tensor product. And then I just use this cochain map and get a map Okay, so to get the product on cohomology, I first pass from cohomology of X, tensor cohomology of X, to the cohomology of the tensor product, and then apply cohomology to this arrow. Does this make sense? Lisa. Okay. Well, here I took singular chains and singular cochains with Z coefficients, but as this observation tells us, I may as well replace R with replace Z with R everywhere, and for example, here I can take hom into R, same here, and so on. Okay, so are there any questions? This is the philosophy behind the product in cohomology. But now this philosophy is this philosophy for the moment contains one black box. Namely, these two arrows are not, we don't know what they are. Well, once we know the origin of the cup product, there is nothing wrong with having an explicit formula. Okay, suppose I have two cochains, phi and psi. And I want to calculate the product of the two. To calculate the product, I need to specify its value on every singular simplex. Well, let me take a singular simplex. Let me call it sigma. This is a map from delta p plus q to x, a continuous map. I know how to apply the first cochain to the front face, and I also know how to apply the second cochain to the back face. Now, do the words front face and back face make any sense? No. Okay, so well, let's start with the front face. I take delta p and map it into delta p plus q as the front p face. Alice, does this arrow make sense? Well, the second arrow is given. It's sigma. So now we understand what this thing is. It's a singular p simplex. Well, the same explanation is valid for the back face. And the back face is a q simplex. Now we know how to calculate this. We know how to calculate this. What about the product? Well, this is just the product in R. We know how to multiply elements of R. Why? Because R is a ring. And this is it. Actually, one can, if one wants, use this as the definition of the cup product. But if one doesn't have the underlying philosophy, then one is basically left with a messy formula which works for mysterious reasons. Now, the reason the formula works is this diagram. And Well, let me state some properties of this particular cup product. I said this particular cup product. Why? Well, because we did make it, all maps in this diagram are functorial, or meaning they're all functorial, but all maps are sort of uniquely given, except for these two. Here we have some choices to make, and there is a particular choice which is called the Alexander-Whitney diagonal, which leads to this cup product, and we will see the properties of this cup product in a second. But there are other choices. Now, one particular advantage of the Alexander-Whitney diagonal is that we do get an associative product on the chain level. More precisely, if R is associative, then so is the co-chain ring C upper star of R. C upper star of X, comma R. Well, the second property, if R has an identity, so has C upper star of X, comma R. Well, the next thing one would want to wish for is this: if X is if R is commutative, so is C upper star of R. Of X comma R. But this is wrong, absolutely. So. But we do have some kind of commutativity, nevertheless. For example, the first good news is that H upper star of X comma R is is still commutative. Well, here I say graded commutative instead of just commutative. Does the phrase graded commutative has any meaning whatsoever? So Wei says yes. Sorry, what's your name? Tagir says no. Alice has abstained. Okay, so yes, so what does, actually you do know this, but you don't know that this, this name belongs with it. This means x times y is the same as y times x. But times -1 to the degree of x multiplied by the degree of y, where x and y are homogeneous components. Homogeneous elements. Which means even elements commute with everything in the usual sense. But odd elements anti-commute with odd elements. And this is something which could be viewed as a fundamental property of the universe. Well, there's an interesting story behind this. For example, if one takes R to be a field of characteristic 0, then one can replace C upper star of x with something which is called polynomial differential forms. Well, let's be more specific. Is R, if R is R, the usual R, the real numbers, and X is a smooth manifold, we can take just the usual differential forms, and those are commutative. Those are commutative on the nose. On the other hand, if we take a field of characteristic P, where P is a prime, then one can show that there is no way to make all these C upper stars into strictly commutative algebras, even graded, well, of course, graded commutative algebras in a reasonable way. And the obstruction to this, one obstruction to this is given by the Steenrod operations. And so on. So the fact that C upper star is not strictly commutative is well, at least in general, is something which is something which is responsible for many complicated questions in algebraic topology. So Okay, so the algebra C upper star of X is not commutative on is not graded commutative on the nose, but the homology is. A side remark. Which is something good to know, but we will not be able to look at this in any detail. There is something which is called an A-infinity structure. Briefly, an A-infinity, sorry, E-infinity. A-infinity exists also, but we want E-infinity. E-infinity is something which is responsible for, which describes things that are not commutative on the nose, but commutative up to homotopy. And all sorts of higher homotopies which occur when we try to do things with homotopies on the previous level. So C upper star of X for every X is an algebra over is an A-infinity algebra. There are lots of models for E-infinity, and there are well, some which are better and some which are worse, but there is a way to choose an E-infinity. Well, there is a way to view an E-infinity structure on C as the multiplication, which is given here, and some number of higher multiplications, which are given by formulas, which are more complicated but essentially similar. And a remarkable theorem says that two spaces are homotopy equivalent. Two simply connected spaces are homotopy equivalent if and only if their singular cochain algebras are quasi-isomorphic as E-infinity algebras. So, in other words, an E-infinity structure, on the one hand, is related to commutativity, and on the other hand, it knows a lot. For what it's worth, again, this was a side remark, and it's safe to ignore it. Now, another thing which I need to say is that let's call this property 1, property 2, property 3, and property 4. The multiplication is a map of chain complexes, or cochain complexes. And well, basically we constructed it in such a way as to get a map of co-chain complexes. There is only one thing I swept under the carpet. Remember the two arrows going in opposite directions, which used to be here. I didn't write what they are. And I only said that there is a particular way to choose one of them so as to get formula which used to be here. And this is the only thing I didn't really spell out. But once we believe this, then we immediately see that the map we get is a map of chain complexes, meaning where phi and psi are homogeneous elements, and the cups denote the cup product, which we have just defined. Okay, now properties 1, 2, one, 2, and 3. Sorry, 1, 2, and 4. Okay, let me be let's not get ahead of ourselves. Properties 1 and 2 are straightforward from the definition. Well, what is 1? One takes every singular zero simplices to 1. No surprises there. Now, property 4 no, property 3. Property 3. Well, we need to remember the diagram. The diagram we had. Okay, so I think I need to finish soon. Okay, properties 1 and 2 are straightforward. So is property 3 and property 4. No. Properties 1 and 2 are straightforward. Property 4 is also straightforward if one believes that the explicit formula which I wrote at some point is obtained by using the diagram. Property 3. Let's talk about it next time. Let's not overdo it. Enough is enough. Are there any questions?
Just probably I missed something, but I would like to know if the upper star XR is already commutative as well, or it just doesn't have any ring-like structure.
Well, no, it is a ring, but as I've just said, there is no way to make this ring graded commutative in the strict sense. Only up to homotopy, and then there will be higher homotopies as well, and homotopies between those, and so on and so forth. And all this together is an E-infinity structure. We don't need actually A infinity because we have strict associativity on which works on the nose. But we do have problems with commutativity, which vanish in characteristic 0. Are there any more questions? Okay, well, let's call it a day.